Thank you. So, hello everyone. Today I would like to talk about some work that I did in an internship earlier this year at Laboratoire Méthode Formelle with Frédéric Blanqui, where I basically got paid for 4 months to prove that the length of a list is equal to the length of a list, so that's quite nice. But before talking about that, a little bit of context. We are using a tool called HOL2DK that was written by Frédéric that translates whole-light proofs to Rocq. But to do so, we translate absolutely everything. So for example, if we have a theorem talking about lists and the length of a list, it would be translated not to a theorem talking about Rocq's length of lists, but instead about a new object that is the translation of the length of a list from whole-light. But we'll see how we can remedy that by talking a little bit about how whole-light defines objects. So there are two kinds of objects in whole-light. There are types, which are at the base there are two types. So the type of Booleans and the type int that is axiomatically infinite. Booleans are there for the logic. And there's the arrow type constructor for functions. But then if you want to create any new type, there is only one possibility, so that's basically everywhere in whole-light. That is the notion of subtype. So if you have a predicate P on a type A, whole-light can declare a new type B, and as well as two functions between B and A, and axiom stating that these two functions act as an isomorphism or bijection between B and the set of elements of A satisfying P. So already, if we can replace these lemmas, these axioms by lemmas on a new type and new functions, stating that they are also bijections between this type and this set, then we can replace everywhere also in the proofs all use of these axioms by these lemmas, and we can replace therefore this type by a new type that we want. So that's useful, and also for objects, what whole-light does, so for terms, sorry, what whole-light does is it can declare a new object X and add a new axiom that states that this object is equal to its body. So usefully, in our proof case at least, that's used instead of some form of unfolding. Instead, it's just always rewriting this equality, which means that X could in fact be anything as long as we have this equality. So again, if we can prove equality, we can replace the object. And so also one interesting function for terms that is relevant to this work is the epsilon choice operator that given a predicate P on a type A has value in A, and there is an axiom stating that if P is satisfiable, then epsilon of P is satisfying P. So it's a choice of an element satisfying P. So that's some form of choice axiom. In general, we are in classical logic. So with whole-light, we have we use proof irrelevance, functional and propositional extensionality, which is going to be very useful to prove equalities between functions, as well as excluded middle, for example. And so now that we know that, our goal, if we want our theorems to talk about length of a list in Rocq, is to prove that the length functions from both systems are equal. But if we want to do that, we would need to first prove that the list types are isomorphic. And to do that, I will need to talk about how inductive types are defined in whole-light. And also these are defined using inductive propositions, because propositions are not types in whole-light, this is different. And in all of that, so this gives us the following plan. Which is that I will first talk about how to align inductive propositions and how I automated that. Then I will explain the way inductive types are defined in whole-light, and then I show my tactics to align automatically inductive types and total recursive functions to do everything that was needed in this slide automatically. Also, I will talk about a bit more, like for example, the fact that I also worked on partial functions. I'll see what I mean by that. And I'll also, with time remaining, talk about what I want to do more in my internship, my PhD, sorry, that will be starting in October. So let's start first with inductive propositions. So for example, let's take the finiteness predicate on sets. In whole-light, it will be defined by its induction principle. Actually, it's going to be equal to its induction principle. You can see that as some form of top-down definition. And the thing is that this induction principle is not actually the same as in Rocq. So instead of having implications and forward quantifiers that you would usually have, instead in Holite you do have disjunctions and existential quantifiers. So to prove equality, what we'll do is basically uh, use propositional and functional extensionality. We'll do induction on both principles, but then we'll have to show how they are equivalent, although they are defined differently. So I won't really talk about what the tactic does because it's quite similar to the tactic for inductive types. But here's how the proof would be done, was done originally by hand. Uh, Not too hard, but also not so trivial that it's one line. And now I define the tactic in the line that allows to do this kind of proofs automatically. So that is the tactic, but then here are some other examples of the use of the tactic. So in the logic library from Holite that I translated during this PhD, making good use of all the tactics that I had defined. So for example, prenex and universal formulae in first order logic are defined inductively, and the alignment can be done automatically. So that basically the definition of the predicate, if I'm not using a specific library, it takes longer than the proof that it's equal. So inductive propositions are used to define in Holite the following type. I'm not going to discuss how it's actually taking place to be defined in Holite, but what matters is that they managed to define this type, Rec space, that you can see as some form of type of trees. So you have uh, this could be leaves and this could be nodes. So with information of type n times a, so data of type n times a and countable branching, because we have a sequence here, a recursive sequence. Um, but then what really matters is that in fact, this const function is really, as it indicates, it's used to define constructors. So to define a constructor, you have a number for the constructor, because for each inductive type you want to separate to be able to separate each constructor. You have non-recursive arguments, so external arguments stored in a type A that is anything. So in general, it's going to be a product of the types of all external arguments of all constructors. And then you have the recursive arguments, which are going to be stored in this sequence, but there are going to be only finitely many of them. So actually, this is going to be it would be better for Light if this was lists, but actually lists are not yet there yet because the rec space is going to be used to define lists. So lists is represented in sequences. So here is an example concretely how it works. So if you have the type of list, it has two constructors. So the constructor of the empty list, in that case, is the first constructor, so it would be attributed to the number 0. It has no external argument, so it has a default value. You can define a default value with epsilon. Noted that in Holite types are pointed, so they are default values. And then no external argument, no recursive arguments as well, so an empty list. Const is the second, so number one external argument A, and one recursive argument stored in a list with one element. So if we want to prove that an isomorphism, we need to show to create two functions between the type of list in Rocq and the type rec space of A, such that basically we have a bijection with the elements that have this form. This is definable with an inductive predicate. And it so happens that we just defined one of such function. This is the representation of lists in rec space, so this is the correct function, defined recursively. And so for the other function, the other way around, we want the inverse of this test function. And well, since we have access to epsilon, well, we can just use epsilon to define this inverse. So we can just take an element x for any r, such that test of x is r. The useful part of this is that since mk is defined with relation to dest, it means that our constellation lemmas will instead we will be able to replace them with lemmas only talking about test. And so that's two theorems that I proved. And in particular, this means that this first lemma is equivalent to proving injectivity of test. This second lemma is similar to proving surjectivity of test, specifically uh, that it's surjective if and only if we satisfy the predicate P. And so now that I have that, the tactics, what we want to do is to prove these two injectivity and surjectivity. So here is how it would be done beforehand. So as you can see, the goal is not that you read that. It's a bit long for just the type of lists. So I think it's quite useful that with my tactics, it's now quite shorter. Not entirely automated though, as you can see. So let's see what the tactic do. Um, so for injectivity, so to prove first I apply the lemma, then try this tactic for injectivity. So we will do induction of both elements because we want to prove dest of x equals det of x prime implies x equals x prime. We're doing induction of both x and x prime, and then dest of x equals dest of x prime will be translated into const because all the image of the function is always in const of something. And usefully, you see this definition for Rec space. This was not the original definition in Rocq. It was done with some form of subtypes. I did that alignment manually to align it with an inductive type, which means that now const is a constructor, which means that actually this equality I can just do inversion to get anything I want from it. So I get equality between the integers in between the external arguments, as well as between the lists. So since they are not really lists, I need to apply a theorem, an additional theorem for injectivity of the representation of lists in as sequences. And then with these are recursive arguments with some with the induction hypothesis that is somewhere in the context. Normally the goal is proved, which is the case here. Just a tactic. For surjectivity though, well, again, that's the goal that we want to prove. So in both ways, what we want to do is do some induction. So either induct on P, which is an inductive predicate, or induct on X, which is an element of an inductive type. If we do induct on X, so that what we want is to prove that P of dest of X, we can use that. That's basically a tactic that I also used to prove in my inductive proposition alignment tactic. I use a tactic called break goal that I defined, which basically does the same as IOTO. It works quite well. And the thing is, before using IOTO, it goes deep into the goal so as to save a lot of time because we know that we want to go deep anyway. And so that can be done with that. But in the other way around, the problem is what we want to prove is there exists an X such that uh, uh, dest of x is equal to r when r is one of the possible values, which is normally, for example, in that case, it's going to be one of these values. So each time it's going to be very obvious what x should be. It should always be one of the constructor of the type applied to some elements. But the thing is that I'm using LTAC, and in LTAC, we do not have access to a tactic that can say instantiate this existential quantifier with one of the constructors of the type. So that has to be done by hand, but it's pretty trivial. That's what is done here. You do exist with one of the constructors, and maybe also rewrite some induction hypothesis, but that's it. Or something. No. Anyway, basically it's trivial. And okay, so this tactic also work with other cases. Here is the type of first order formulae in the logic library. And again, quite compact to align, especially since, it's 4 constructors, so it would be even longer than what it took for lists to align. So useful. And then, well, once we are there, we have aligned lists. We can go on to trying to align the length. So here is how recursive functions are defined in HOL Lite. Simply, you just need to specify each equality for each constructor. So that's conjunction of equalities, and then you use epsilon to pick one such function. Okay. But also you see there's this unnecessary variable that is probably used somewhere in HOL for labeling, so it's used nowhere in the definition and it's instantiated right after with this six-tuple of integers, and it's actually quite annoying to deal with that in the when you want to prove things, because actually I simplified it for you, but actually these numbers are represented this way. So for something so unuseful, it creates a lot of space. But thankfully, so if we want to prove something is equal to epsilon, I think it's quite sensible. What we are using is a theorem stating that if our object satisfies the predicate P, and if P is uniquely satisfiable, then our object is equal to epsilon of P. Logical. Um, but then what's useful is that I'm using a tactic, align epsilon, created by Theo Winterhalter, that does both applying this theorem and also completely getting rid of this unnecessary element from the context altogether by applying some useful transformations. And then basically my tactic, what it does is only focusing on automating the proof of uniqueness by induction quite easily, because otherwise the fact that the function, for example, length satisfies the equalities is actually basically reflexivity in Rocq, so nothing to do. So again, we can prove it totally automatically, and here are two other examples. If you take a formula and want to see all functions or predicates in it, you can define it recursively, and again, the alignment is automatic. Except there, this is just because the definition is actually a little bit different in terms of set definitions, but that's not very important. Okay, so once we do that, let's talk very briefly about partial functions. For example, the head function on lists. What is the head of the empty list? In Rocq, it's any default value that the user wants. In Highlight, you don't even need to specify it because with epsilon, it picks one function. And so the value on nil is not very important. And basically, aligning such functions is quite similar to before. It's just more complicated because the problem is now that epsilon, this predicate is not uniquely satisfied because we don't know the value on nil. So my tactic has to deal with that. But it works the same, it works well. I also gave some tools to work with defining sometimes um, partial functions upon using if then else over propositions with our axioms. We can do that. And okay, so I also did some work about that. But then anyway, we really did everything that we wanted to do, so I'm quite satisfied with my work in this internship. The alignment of everything up until length is well automated. And also I did a bit of additional work. So I'm going to talk very briefly about what I want to do next. So first of all, remember the surjectivity was not automatic, and also I said defining the correct object was sometime longer than aligning. Well, both of them, I believe, and I'm quite confident, I will be able to do with some metaprogramming. So now I've started, I'm only at the beginning, but I've started writing some tools for that in RockLP. And so that basically, hopefully, the goal would be to be able to align by one command, maybe multiple objects fully automatically, and also sometimes defining the correct functions to do that in just one command. I think I can do that, and that would be really useful. And also, quite important, currently what we do is we do the alignments, and then we translate the proofs with the translated objects. Which means that every time we change the translation, we need to retranslate all the proofs. And for example, in the multivariate library, the proofs are around 90 gigabytes. So we really don't want to translate them and recheck them. It's quite long. So the idea that I had is actually do the alignments after the translation by using some generalization using type classes. So for example, I have a class for a type of list that satisfies all the axiom of lists in a light. Same for definitions. And then the theorems are going to be general on these by simply using the section mechanism in Rocq, which means that afterwards we can do the alignments by just creating instances of these classes and apply the theorem like we would normally do. So there are multiple ways to do that that I'm developing, and I want to do that a lot during my PhD. And it's actually also one way it is useful is because, well, if it's so long to translate proof and it would also be quite annoying, we do not use the theorems in Holite for our alignments, but it's actually quite useful to use them. So by doing that, I coded a tool to do this automatically with OCaml. And actually, I can say that I can save multiple hundreds of lines of code of alignments just from using some Holite theorems instead of reproving them. And that's actually really useful. So I'm really eager to continue doing that with the next with my PhD. And for now, thanks for listening and thanks for having me here at the Rocqshop.